All right, to get full screen, looks like we're doing lesson set 28. Most of these problems you've done now 3-4 days in a row. There's a couple tacked on at the end that we haven't seen quite as much, but hopefully we can gallop through this and gain a little more experience and understanding. All right, so Renee is ready to move. Let's get lined up here. Rational function, you know the drill. Y, K, T, D, you know the drill. If I put that down, my expectation is you've seen it so much, I shouldn't have to tell you what to do. All right, so we got ourselves a graph. End behavior. We're both to the first power, so it's 2 divided by 1. We're going to 2. You want to verify that, put a big number in. Put 1,000 in. 2,000 minus 6 over 1,000 plus 4. And when you're approximating, I think you can eliminate those little changes, and the big change is 2,000 divided by 1,000 or negative 2,000 divided by negative 1,000. So y equals 2. We're going to get sign changes at x equals 3, which gives us an x-intercept. That's the only way you can make this fraction 0. When you let x equal negative 4, you're undefined. So x equals negative 4 is undefined. You can spot the y-intercept, negative 3/2. 0 gets us negative 3/2. And there's our trajectory. And there's our graph, given the fact that we have a sign change at negative 4 as well. See the difference when you plug in negative 3 or negative 5? Doesn't really change this. This is still a negative number, but the denominator does change signs at negative 4. So what used to be negative, huge negative numbers are now huge positive numbers, especially if you drop in a number like negative 4.001 and see what happens. And that's how you're going to gain understanding, is by plugging in the numbers and seeing what happens, and then getting a feel for the shortcuts. So from a numerical standpoint, when I drop negative 4.001, I get a negative 0.0000, I don't know how many zeros, but I get a bunch of them. And when I put negative 4.001, I think I can approximate. -8 minus 6 is minus 14. That is fitting into that an inordinate number of positive times. All right, and then if I did 3.99999, negative 3.9999 coming in from the larger side, that's a larger number than negative 4. Coming in from the larger side, I can see the trajectory is going to negative infinity, the sign change. So put a big number in, you're getting close to 2, put negative 4, heading towards negative 4 from the left, positive infinity, heading to negative 4 from the right, negative infinity, heading to 0. Well, now that's another matter. A little more discussion about limits. Doesn't matter whether this coordinate exists or not. The limit is the trend towards, and I can definitely see that as I'm moving towards 0, I'm heading towards this number. And if my numbers are coming down, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1.001, I'm heading to that number. So the coordinate itself does not need to exist. How could I get that coordinate off the board? By putting in another factor and writing this as x times that and x times that. And the original problem would have come your way as y equals 2x squared minus 6x over x squared plus 4x. And then we get what is called a point of discontinuity. Point of discontinuity. Most teachers would call it something else. I'm going to call it a removable point of discontinuity. All right, because it doesn't really affect the reduction of the fraction, except that it basically makes 0 undefined. If it's undefined, we can't use it. But you don't get any crazy behavior near 0, because no asymptotic behavior, because we canceled it out of the problem. Now that's a little something new, that you just heard for the first time. So put a smile on your face and wait till you hear it another couple of times, and it'll make some sense. Like hopefully the rest of the lesson said. All right, so we're hopefully going to look at the sine of 11 pi over 4, picture in our head where it is, and write root 2 over 2. All right, 11 pi over 4, I've gone to Google now. I've actually typed 11 times pi over 4 to get a better approximation. Early on, I was just throwing some numbers around in my head saying I'm near here. This is a much near here than what I was doing before. So where's 8.63? Well, you need frame of reference, 6.28. This is 1.57. And if you add that up, you're still less than 8.63. And if you add 3.14 to that, you're bigger than 8.63. We're in the second quadrant. Right? We're about somewhere in the middle. Just a quick feel. All right, now, how do we do this problem? We do the top half of the circle, we break it up into 4 parts. And as soon as we do that, we can see equal parts, which means we have a 45-degree reference angle. We've looked at this a bunch of times, but we'll keep looking at it from different perspectives. One perspective is if they're the same, then we got a half and a half equaling 1. And 1/2 square root of a half happens to be that distance. We're looking for the sine. So we know we've got square root of a half, which is the square root of 1 over the square root of 2, which is 1 over root 2, which if I rationalize root 2, then I get root 2 over 2, which is approximately 0.71. The other way to look at it is to think of this as x, and therefore 2x squared, because that's x squared, 2x squareds add up to 1. And we can get it algebraically by solving that. X squared equals 1/2. There's the square root of a half again. It's a distance in this case, so I'm just going to say positive. But, we're going to get root 2's and root 2's all over the place. All right, so that is a long chat for a 3-second problem. So how do you do it in 3 seconds? You find the location that's closest to 11 pi over 4, which is a multiple of 4, which is 12 pi over 4, and I know I'm 1 less. That's what my brain did. It went here. I know I'm here. I know it's 45 degrees opposite to hypotenuse root 2 over 2. That's what you're trying to master. All right, so now cosine. Cosine 5 pi over 3. We'll do that in a second. I started this yesterday and had to stop again, so I've already done some values, but let's get them from scratch. So cosine of 5 pi over 3 is, cosine of 5.23. Let's figure out where that is. Okay, up. So good number to know is 4.71, 6.28. So how far is it? 0.23 and 0.29, 0.52. 0.52 more radius distance. Okay, so where does that put me? Puts me in a triangle like that. That's pretty good drawing. And we've been looking at 0.52 in the last few lesson sets, and that's the one that gives you 30-degree change, 30-degree units of change. Can't write a number 3 here this morning. 30 degrees, which is actually that angle. So our reference angle is 60 degrees. You're trying to have that triangle memorized in your head. Those are our ratios. So we're looking cosine. Cosine is the width, adjacent over hypotenuse. Hypotenuse always stays the same, so 1/2. That's what we're going to be doing. Tangent of pi over 6. Well, 30 degrees is pi over 6. So I think we can cut right to the chase here. 0.52 radians, a little bit more than half a radius length. So let's get a circle. There's a radius length, marker distance. We want about half of that, right about there. And that should look like our 30-degree angle. Half. Root 3 over 2, 0.87, 1. Now, Instead of dividing by half by root 3 over 2, I think it's useful to have this picture in your head, double the size. So right now that was a half. I'm doubling the size, doubling the size, which makes it a 1. That therefore is root 3 over 2, doubled is root 3, and doubling the radius. Okay, so what is my ratio? If x is my angle, what is the sine of angle x? A 1 to 2 ratio. What is the cosine of angle x? A root 3 to 2 ratio. So what's the tangent? 1 over root 3. Which is approximately 1 divided by, I hope you know root 3 is what we're using, 1.73. All right, so somewhere between a half and 1. 1 over 1.73 is somewhere between 1 over 1 and 1 over 2. That number's between those. Okay, next problem is a recycled problem. You did it 3 or 4 lesson sets ago, I believe. So, and 0 to 2 pi is basically just letting you know we're talking about what angle in the unit circle is going to make this a true statement. So -1 becomes +1. Multiplication by 4 becomes division by 4. Squaring becomes square rooting, so plus minus a half. That's the square root of the 4th. And now we're here. Okay, I'm giving you the ratios this time. I'm looking for what? The angles. I know the sine function never gets bigger than 1, smaller than -1, and in the middle is 0, and I want a half. Looks like that's halfway up, that's halfway up, that's half, and that's half. And as we keep doing these, we want these triangles to pop up in your head. So pi over 6, all the odds, 3 pi over 6, 5 pi over 6, excuse me, 5 pi over 6. I was talking about the odds, but I just started counting odd numbers. 7 pi over 6 and 11 pi over 6. Now, looking at those values quickly, 1 period of the sine function, there's 1 period. Where's halfway up? That's 1. Halfway up is there. Hope you can see that 30 degrees makes some sense. 90 degrees gets us 1. Where's the next half? Right there. And that's 30 degrees before 180. All right. Pi divided by 630 times 5, 150. So that would have been 150 if we were working in degrees. 210, 330. Pause the video. If you want some more time with these problems, pause the video. I'm just going to keep talking. What's the period of this function? Pi, just looking at it. That's where I looked. What did I look for? I looked for that. Okay, and that multiplier is 2. And therefore, divide that multiplier into 2 pi, and you've got the period length 3.14 units. Everything's going to happen in 3.14 units that normally would have happened in 6.28 because I'm doubling where I am on the circumference of the circle. So things are coming at you faster. So if this is 6.28, this is now 3.14, which we will call pi. I'm going to leave that number out there. All right, that x value is 6.28. This one is pi. And at pi, I'm going to get 30. And at 3, at 3, I'm going to get 30. Didn't look at the rest of that. So therefore, what do I have here? I have 3 plus pi, 3 plus the period. 3.14 units is going to get me back to 30, which means that 3 plus pi over 2 is that one. And this one is 3 plus pi over 4. And 3 plus pi over 4 is going to get me 7 on top of 30. Okay, normally we do this, yes? And 6.28 is out here. What would have happened in 6.28? I would have gotten another, well, I got to go further than that. I would have gotten another period. Okay. Would have been 3 plus 2 pi. Would have gotten me back to 30 again, so on and so forth. Okay, enough of the discussion there. What's the range? y value is less than or equal to 37, greater than or equal to, take 7 away from 30, 23. Useful to know that as well. All right, so I put some things up on the board here. Getting back to this, I did this yesterday a little bit, and then I didn't do the video because I got interrupted again. So where am I at here? I'm at, oh, period, right? Okay, so you're gonna take x minus 2 over 3. I know I asked my students one time in calculus what kind of function they were dealing with here, and I didn't get too many answers that sounded linear-like. I don't think I got any. All right. So I'm just highlighting it because what's the rate of change? Another way of writing x minus 2 over 3, and we've been practicing this. 1/3 x minus 2/3, dividing into both. And dividing by 1/3 is the same as multiplying by 1/3. Okay, so now if I drop that number, that multiplier, into 2 pi, I get 6 pi. All right, so this, if I'm walking around the circumference of the circle at 1/3 the rate of the normal movement, and I don't know if that makes any linguistic sense, but compared to the parent function, things are taking 3 times as long for a revolution. Sounds like a history class. Okay, so students, if they realized that this was 1/3 x minus 2/3 and it was a linear function, then they could have done the integration, but got stuck there. Okay, so let's get unstuck. Boom, boom, boom. What makes a 0? 2. And cosine of 0 is, I haven't started walking around the circumference of the circle yet. I draw the triangle. Pretty hard to draw the triangle there. It has width, but it doesn't have height. And cosine measures adjacent to hypotenuse, which in this case is 1 to 1. So actually, 1 period of the cosine parent function starts at 1 and goes back to 1. 0 gets me 1. 1 gets me 0. I'm sorry, 2 pi gets me 0. 2 pi gets me 1. You can tell I'm waking up. Get me that coffee. Where am I? Oh yeah, sun's coming out. I finally got that stated properly. Now what's changing? Well, I don't go from 0 to -1 and 0 to 1 anymore because I've moved this curve up 4 units. I've increased every value by 4, and I'm increasing the magnitude by 5. And those are the key numbers. And I'm starting not at 0 anymore, I'm starting at 2. And I know the period here is, what did I say, 6 pi? So I'm moving in that direction, 6 pi from what? From 2. From 2, I'm moving 6 pi in that direction. So therefore, I'm ending up at 6 plus 2 plus 6 pi. And then I'm back to 9. Let's see how that one works. Let's put 2 plus 6 pi in for x. All right, now why was that there? I don't remember why I put that there yesterday. Okay, oh no, it's gone. So many things are gone now from the old noggin. X minus 2, so therefore I am looking at 2 plus 6 pi minus 2 over 3. That's all we need to look at. Okay, so what happens? The 2's cancel. 6 pi divided by 3 becomes 2 pi. And what's the cosine of 2 pi? The end of the first revolution of the parent curve. All right, good enough. Had another discussion about that. More things to think about again repetitively so that they hopefully find a place in the old noggin, nice comfortable place that you can access quickly. All right, 6x cubed minus 18x squared minus 4x plus 5. All right, I did put some things you must know about cubics. You must know that minus b over 3a, the average of the roots. I did a video about putting cubics in graphing form, and I used 0, I used 2, and I used 10. And the graph looked like this. Okay, where's the point of inflection? Right there. Happens to be at 4. And it's because 0 plus 2 plus 10 divided by 3 is equal to 4. And that's all about completing the cube, using different dimensions of a box, evening them off, adding them up, evening them off. That's what you do with completing the square. You take two sides of a rectangle, you even them off until they're a square. Doing the same thing here geometrically. If you want to see that happen, look at the completing the cube video. All right, and explains why that happens from a geometric standpoint. So minus b over 3a is representation of the average of the, to make this a perfect cube. And then you still need the remnants of it in the formulaic creation of the graphing form. All right. Minus b, 18 divided by 18 equals 1. So I now know that I've got x minus 1 cubed. I got a perfect cube. I'm going to get rid of some of the things that we don't want over here. Now I got to plug 1 in. That's 6. That's going to be minus 18. It's going to be 3 times the opposite. Always is. Double this number, right? So I could have gone immediately here, plugged in 1, gotten 6, doubled it and changed the sign, and I wouldn't have to do that. Minus 4 times 1 plus 5. Looks like I'm adding 1 to negative 12, gets me negative 11, and I'm calling that HK. I'm calling the point of inflection HK the same way we use H and K for the vertex of a quadratic. So that's the K value. That's minus 11. I know the A value, 6. The only thing I'm missing is the correct number here to eliminate error in this calculation. And the way you get that is C minus 3AH H squared. That gives you the rate of change at the point of inflection, which saves you having to do a first and second derivative in calculus. So C minus 4, minus 3. A was 6 in this case, H was 1. So I'm getting minus 4, minus 18, minus 22. That should be the same thing. That should be the same graph. But it allows us to see what's going on. So we start with shape. I know the shape now is one of these because that is negative and this is positive. So therefore, if this was all positive, then I've got a function that's just always increasing. But the interplay of these terms dictates where I am on the graph, the changing rates. And I now know that I am at 1 comma negative 11, and I'm going down at 22 to 1. I also know that I'm at a y-intercept of 5 and I'm going down at 4 to 1. So therefore, I've got to be on this side, and that is 0, 5, and I'm going down at 4 to 1, and we've looked at y in previous lesson sets, so I'm not going to go over that here. But it tells me that my x value for that min should be a little bit less than 0. How do I find that x value? And you're going to hear these every day till May 15th. So you don't have to learn it right now. But the sooner you start to memorize these, the sooner you will get correct answers. So H in this case is 1. I'm doing minus, very similar to quadratic formula stuff here. The opposite of M. Well, the opposite of minus 22 is positive 22, divided by 3 times A. A is 6, so that's 18, and I'm taking a square root. And now I know that x value. Now, for the record, 22 divided by 18 is a little bigger than 1. The square root of 1 is a little bit bigger than 1. And if I take a number a little bit bigger than 1 from 1, I think I'm to the left of 0. Okay, so what's this one? This x value is 1 plus the square root of 22 over 18. Okay, got a lot of information in front of us, and honestly, without talking to you, probably do that in 60 seconds or less. That's pretty good without a calculator to find the x value of a point of inflection and the rate of change at the y-intercept, all within 60 seconds. Yep, I think that's pretty good. So I want you to learn it. Direct, inverse, and joint variation. Review of Algebra 1. Direct variation, y equals kx. So let's get some numbers here. Do I even have the number that you worked with? Does it matter? No, it doesn't matter. So whatever's on the sheet's on the sheet, but let's say X is 5 and Y is 10. Okay, so what's this? 10, what's X? 5. Do you think we can solve for K? I do believe we can. We now know it's 2. So let's just change we now know K is 2. Let's say we don't know what Y is, but X is 6. Okay, I think 2 times 6 is 12. That's the kind of work we're doing here. And the only way you can get that wrong is if you're not doing any homework or any work in class. All right. Next, inverse variation. Y equals K over X. Let's say X is 2 and Y is 6. Then 6 equals K divided by 2. I now know that K is 12. If I change one of these numbers, make that 4. Remember, a 2 got us a 6. Now a 4 into 12 gets us 3. Because we just found out that that's 12. And a 4 gets us a new number, 3. What can I see? My Y values went down. What can I see? My X values went up. That's an inverse relationship. Joint. I'm not going to do the X's and the Y's. Just going to practice writing it. Joint variation, Y equals K. Start with there. Constant of proportionality. We told you how to spell constant. Yep. Yasser agreed. So we're in good shape. So cubed and inversely as X cubed. Jointly as X cubed and the cube root of Z. And we're headed towards some science formulas here probably. All right, so that's joint variation. All right. Now let's talk about cubics for a quick second here. Got to move Rene Descartes. Going back, I should have brought this in. I'm going to leave this. Try to get a better drawing at some point. There we go. Let's get back here. Just pointing out, I think we need to look at this table and look at this table quite often. Here's a cubic parent function, y equals x cubed. And we can see it's changing least quickly right there. Everywhere else, every tangent to the curve is positive, except for right there. Now, why is that? Well, it's all about tangents are all about rates of change. Let's look at 3 cubed again. 3 times 3 times 3. I guess it's those threes. Gets me a volume of 27. What happens if I standardize moving the dimension to the right a little bit by adding 0.01? All right, every single dimension just changed by length, width, and height changed by 0.01. And if I do the math, how many decimals did I get here? 1, 2, 3, 4, 5 decimal places. So therefore, 1, 2, 3, 4. I just did 5 decimal places. If I threw that in a calculator, well, I don't need to throw it in a calculator because I'm doing it with calculus in the brain here. I get a change of 0.00027. Whereas at 0, if I cube 0, I get 0. But if I cube 0.00001, I'm going to get 15 decimal places. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. NASA stops at 8 decimal places. That's enough accuracy to be sending people out in space, I guess. At least that's what I heard. I'll have to check it. I got a buddy who worked there for a little bit. So we got, I don't see any change. Oh, and the slope of the tangent there is 0. No kidding. That's a minimum slope value. Whereas every other one of these is changing more and more quickly. Why? Well, look at the numbers. It's really surface area. I should have brought my manipulative in. I'll bring that in the next time. It's really, we've got surface area here. There's no box here. There's no box. If there's no box, it's pretty hard to change the volume by changing that by 0.001. All right, we'll develop that conversation as we move along. And Rene is ready to move along. And we just want practice here. L in a 30. What's the L in a 30? L in a 30 is It's going to be 0.7 plus 1.1 plus 1.6. So it's approximately 1.8, 3.4. Now keep in mind, doing the inverse of e to the x, which is what ln is, a little change in x here makes a massive change in y here. So as these numbers get bigger, our ability to approximate goes out the window. But locally, it's pretty good. And therefore, we can learn our rules of logs, which is what we're after right now. All right. We have been practicing writing 30 in E notation, which is going to come from 2 times 3 times 5, which is what I just did in my head up here. 2 is e to the 0.7 times e to the 1.1 times e to the 1.6, approximate. This is an approximation. And that is approximately e to the 0.7 plus 1.1 plus 1.6, our rules of exponents. Logarithms only look at the exponential activity. All right, the ln of 30 is what do I put on top of e? What do I put on top of e to get this statement? And that is, the ln of 30 is exactly equal to the ln of 2 plus the ln of 3 plus the ln of 5. And if you look at these numbers, 2, 3, and 5, that was multiplication. Those numbers were being multiplied. These numbers were being multiplied to create this addition of exponents. So now, powers and roots, 3.4 is 34 divided by 10. If I have a number, e to the 34 over 10, I think I'm taking the 10th root of, I think I made a misstatement here earlier, maybe I did, I don't know. I'm taking the 10th root of e, where am I now? Of e to the 34. There we go. That could have been expressed this way. Interesting. All right, hope I didn't make any misstatements there. Let's do another rational function quickly. And I'm just going to zip through the, what do I want to call it? The steps. All right, we want to get this down to, let's do the same steps every time. Okay, what's a good first step? Take what's given. What's given? Everything we need to know. I think we should put this in factored form though. 2 times x minus 1. Let's use both of those. Okay, what do I see? I see that there is no y-intercept. If I put in 0 for x, it's undefined. So therefore, I'm going to get rid of this for the moment and say that at x equals 0, undefined. But if I put a number like 0.01 in, well, it's also undefined at x equals 1. So maybe we do this. Okay, there's my origin. Undefined. All right. So what happens when I put in a number like, so this is one that you can't reel off quite as quickly as the others. You got to do some thinking here. So what's this? This is pretty close to 0. 0 minus 1, pretty close to minus 1, times this number makes it negative 0.001. And how many times will negative 0.01 go into 2? Lots of negative times, so it does that. I know there's no x-intercepts. Judging from this, I know there's no way to make that fraction equal 0. You can try. You will not be able to make that fraction equal 0. So therefore, it does not cross the x-axis, which means it's got to go up and come down. We're not going to look at that without a calculator at this stage. So just know that there's a local max here. All right, and ignore it for now. We can find it, but we're not going to do it until later stages of the term. What else do we know? We know that this is x to the 0, which is 1. That exponent's smaller than that one. So therefore, this thing goes to 0. So it goes to y equals 0, asymptotic behavior. Y equals 0 over here as well. Now, is it coming up from below or above? Just put one number in. That's all you need is one number. Throw 10 in here. 2 over 100 minus 10, 90. 2 over 90 When I put 10 in, I got a small positive. So therefore, it's going to do that. You want to verify this? Remember, label your asymptotes. I forgot to here. Let's pick the number 2. The number 2 should give us a better sense of where I want to put this. All right, 2 squared, 4 minus 2. So really, it's a height of 1. So I could probably do that the next time. 2 gets me a height of 1, just to get a little better graph. I'm getting sign changes over here. This is to the first power. Right now I'm negative, so I know it's going to be positive. But for your sake, let's put in a number like -2. Let's put -2 in there. 4 plus 2, 6, 2, 6, 1/3. So I could have done another better job here by putting that in first. And I would have seen it, it's a little bit lower here. 2 gets 1, -2 gets 1/3. So you got to plug numbers in to get a feel for these fractions. There's no way around it. You got to put numbers in to get an understanding of rational functions. So what's the limit of f of x as x goes to infinity? This is about where I stopped, I think, the other day. 0. What is it when I come in from the right? Well, coming in from the right means I'm going from 1 to 1/2 to 1/3 to 1/4, so on and so forth. And we can see that this is headed towards negative infinity when x is 0. So that's negative infinity. What about 1 from the left? Going in here, it's also negative infinity. And how about if I move to negative infinity? I think we talked about this, but let's put a negative number in, a big negative number. A big negative number is going to become a negative minus a negative, but really you're just looking at 2 over x squared. X squared makes positives, right? So we're getting a huge positive number here. Put it in -1,000. -1,000 squared is 6 zeros. So I've got 2 over 1 million. 2 millionths. Okay, it's getting small, but positive. So that explains why I'm writing 0, I hope. All right, running out of breath again. I'm just taking the equations off of the internet. So you pause that, and we're just going to write the equation. So we got 70 at 50%, so that's 70 milliliters. 50% is 0.5. So we got that, and we're going to add some solution at 80%, so that's a 0.8. How much of an 80 must she add? So 0.8, adding a certain amount, and that's going to get me a solution at 60%. We want 60%. So what's the total amount of solution? Started with 70, added x. Okay, got the sun in my eyes. I'm pretty close to the board. I hope talking to you, I didn't really spend any time looking at that, so I hope I didn't make a mistake. But I got backup. So 5x squared minus 20x plus 7. Well, let's have our quadratic chat. The other side of this board. I guess it's easier to move Renee at this point. So let's move Renee over here. Keep talking about some concepts that are very important to you in your future courses. If we start the conversations now, you might gain a better understanding. All right, so how do we change the area of a square? Well, here's area of a square. If I put a border around it, like the frame on a picture, if I put that border on, then the square area has increased. I've got the picture and its frame, and that makes a square. And if I measure that area, it's bigger than if the frame wasn't there. Now, we're going to standardize the increase in dimension. We're just going to talk about it going up by some number, standardized to get a feel, a numerical feel. So in this case, I changed by 0.001. And I did the math, and I got 9.006001. That's how much the frame has increased the area, 0.006. All right, and if I divide it by 0.001, I can see I'm going up at 6 to 1 right there. So in the quadratic at 3, 9 for area, I'm actually going up at a 6 to 1 rate. At 0, I'm not changing at all. I mean, we use tangent lines to give us a feel for how numerical tables are changing. Why am I not changing at all? Well, let's look at 0. Did I even do 0 anywhere? I'll do it here right now. All right, 0 squared is 0. Nothing new there. But what is 0.001? Standardized frame, dimension. If I square that, I get 0.000001. And if I look at those first three decimal places, over here, that's what I looked at, the first three decimal places, I'm not seeing any change. Why? It's pretty hard to frame a picture that doesn't exist. That area, there is no area. Then the drawing of over, down, over, down, over, down gets bigger and bigger as I move to the right, which means that my rates of change are increasing. Turns out at 1, I'm going up at 2 to 1. So at 1, that tangent would be 2 to 1. At 2, it would be 4 to 1. Do you get a feel for acceleration? Because each rate at each user-friendly number is going up at 2 to 1. Now I was talking about a second derivative there. All right, so rates of change are very helpful. And I can see that the rate of change here of x squared is doubling the x value. Remember, 3 got me up 6 to 1. 2, 4 to 1. 1, 2 to 1. That's what the tables are showing over there. So I can see that x squared is going up at a 2 to 1 ratio, whatever that x is. Okay, and I'm multiplying it by 5. If I multiply every table value over there by 5, it's going to go up 5 times faster. I mean, that's really what a linear slope does, right? This goes up at 1 to 1, and I'm multiplying it by -20, which means I'm going down at 20 to 1. So what is the first derivative? We'll do q prime. 5 times 2x, 10x minus 20. Oh, and I think that's a quadratic that's going up. And I think at the vertex, the slope is 0. And this is a formula for slopes. That's a formula for slopes. And when is it 0? When x equals 2. Well, let's do minus b over 2a now. Minus b, 2 times 5. What a coincidence that I now have the vertex from the rates, looking at the rates of change. Just as easy to find the vertex using rates of change. And so plug in 2, and we get 20 minus 40 plus 7. And now I know that at 2, I have, where am I? Minus 20 plus 7 minus 13. Right? And that's from that perspective. Also, the next derivative is kind of what I opened up for a conversation over there. The next derivative, double prime, is simply 10. Right? This is not changing. That's a constant. We've talked about that numerous times. 10 to 1. Okay? But that's positive. What does positive rates of change tell me? Well, here's a rate of change. And if it's positive, I'm accelerating. Okay? So every x, each one is going to be going up at 10 units. Instead of 2, 2, 2, 2, it's 10, 10, 10, 10. All right. So that gives me the shape. All right, the initial conversations, we don't have to have them for long. I'm not expecting you to learn this on the spot. But if we keep talking about it, hopefully the brain will process these concepts and you'll have an understanding rather than just mechanical precision. A lot of students can do calculus mechanically, and then when they get done with the class, they wonder what they did. Okay, you got to connect it to geometry. We're starting to do that. So look at those geometric relationships and you got a good chance of really understanding integration and differentiation when you get there. I fear if we don't have these conversations, you won't. That's why we're having them. All right. Sign chart. When is this polynomial bigger than or equal to 0? When I put different x values in, when will they be positive or 0? Well, we can do a sign chart right now. At 0, I'm going to get a sign change. At 5, I'm going to get, if it's to the first power, I'm going to get a sign change at 5 and 0. And I'm going to get one at -2. So all I need to know is one situation. I'll pick a number bigger than 5. We'll do the sign chart here. Bigger than 5. Well, that's positive, parentheses. Bigger than 5. That's a positive, parentheses. Bigger than 5. That's a positive, parentheses. True or false? True. True, false, true, false. That's what's going to happen. because we're going to get sign changes everywhere. Now let's pick a number between 0 and 5, and we're going to find that we're going to get a sign change here, not over here. Okay, so let's pick 4. 4, still positive. 4, oh, a sign change right there at x equals 5, sign change. 4, still positive. Well, that's false. That is not greater than or equal to 0. False. I'm saying between -2 and 0, you're going to get a true statement because we're going to get a sign change here with the 2x cubed. Oh, -1 cubed times 2, that is a sign change. -1 minus 5, didn't change that one. That's still the same. -1, 3, -3 plus 6, still positive. I get another sign change. So what used to be not true is now true again. True. Oh, yeah. And if you pick a number, and I'll let you do that, pick a number less than -2, you're going to see a sign change. All right. What's quicker than that? Graphing it. So what does this graph look like? Linear cut at 5. First off, I know I'm going up. How do I know that? Well, x cubed, x to the 4th, x to the 5th. This is an x to 5th graph, which means on the right it should be going up, and on the left it should be going down. So at 0, I get a cubic change. We'll look at why it looks like that in future classes. And then a linear change. And there's our end behavior, our x to the 5th end behavior. All right, where am I greater than 0? All of these values produce negatives. These produce negatives. So when am I bigger than 0 or equal? -2 to 0 gets me positive y values, and 5 to infinity. It's important to be able to do these graphs. We'll practice it till May 15th because you're going to use it with those derivative discussions in future classes. And if you can't do it, the teacher has to stop and teach it. And we don't want to have to do that because we want to talk about applications and other aspects of calculus, not the foundational stuff, which is what you're practicing now. All right. Now, this technique is very helpful in finding the domain of functions because we can find the numbers that are critical. X squared plus x minus 30, we will factor. X plus 6 times x minus 5. X plus 6 times x minus 5. Okay, so let's put this in front of us a little more clearly. ln of x minus 3 over x plus 6, x minus 5. Now, the only really three functions you're going to work with a lot at this level: logs, square roots, and division. All right, those are the restrictions. The other functions that we're studying have fewer restrictions on what numbers we can use. What numbers can we use with logs? Any positive number. Any positive number we can work with that calculation. What numbers can we work with for square root? Any number greater than or equal to 0. My numbers have to be greater than or equal to 0. And what can we work with division? Well, you can't work with dividing by 0. So therefore, -6 and 5 are right out the window. So -5. +5, no, can't use. -6, no, can't use. Okay, logs have to be positive. Okay, so the parentheses has to be positive. That tells me I got to be bigger than 3. So I got to be bigger than 3. I can't use 5. So far, that's true. This is no longer a consideration. And bigger than 3 means open circle. All right, and what else do I have? That's it, I guess. I've already done the division consideration. So what is this in interval notation? 3 to 5, union 5 to infinity. That's the domain of that function. So getting good at sign charts is going to be able to get us inequality answers quickly and domain answers quickly as we practice them. One more problem here. Area, oh, I guess we're doing another area problem. So 2x squared plus 12x minus 7. From a derivative standpoint, we'll call this a of x. Then we want a prime of x, which in this case is 4x plus 12. Remember, you're doubling 2x times 2, so you're really just doubling that and dropping down 1. When is that equal to 0? Because that's our slope formula. When x is -3. The second derivative is 4. That's how that's changing. So every tangent, if I have a tangent here, the next user-friendly number is going up 4 times as fast, 4 times as fast, so on and so forth. Hope I said that correctly. And then we can plug -3 in. So we know we have a cup shape up. We can plug -3 in. -3, -36 cut in half, -18, -7, -25. And I also know that I'm going up at 12 to 1 here. All right, so where am I going up? On this side, I'm going up at 12 to 1. When x is 0, the y is -7, so that's the coordinate 0, -7. And we just put a -3 in. We got -25. Doesn't hurt to do rise over run squared one more time. -25 to -7 is 18 units. Squared change, 3 to 0 is 9, and 18 divided by 9 is 2. Doesn't hurt to hear that again. And what's the sign of 31 pi? 31.3. What's the sign of 31.3? Need a frame of reference. My frame of reference is 6.28. That's how many radius lengths it is around that circle. And we're calling our radius a unit of 1. So we're with 31.3. Sure looks like if I multiply by 5, I'm getting close to this. If I multiply that by 5, 5 trips around, 5 trips around. I get a 0 with a 4, I get a 0 with a 4, and I get 31.4, I believe. 31.4. Oh, that's a little bit more than 31.3. I think I'm here. I think I'm pretty darn close. I think I'm 1/10 of a radius length. 1/10 of a radius length. Wow, that's that arc length. I got to blow this up. So I got this and then this. And I'm going to draw a triangle and do that. Well, I think that height is pretty close. Distance-wise, they're about the same magnitude. Yeah, I think Google's going to tell me that if I do the sine of this, I'm going to be pretty close to -0.1. And now that the video's over, once I upload it, I'm going to put that in. And if I don't get -0.1, I'm going to do the video again. Because I'm making a fool of myself for the 99,000th time. And hopefully that this practice is getting you a little better foundation, which will support future levels of study. All right, Yasser, if you can check my work, that's great, because I appreciate it.